cool. So let's get started here. So this first week, what we're going to be covering is this topic, what's called significant figures and unit conversions. This is essentially kind of going to lay the groundwork for how we do math in chemistry. As I mentioned before, this is sort of a math-based course, not in the sense that we do any sort of crazy calculus, but that we do basic algebra. We do a lot of simple calculations, multiplication, division, addition, subtraction, all right? And believe it or not, we got a little bit of a different set of rules for performing these operations in chemistry than you have in your math class, all right? Today, our big topic that we're going to get through is this first one of the week here, significant figures. We'll start in on our unit conversions next class period, all right? So this is the focus of today, okay? Sometimes abbreviated sig figs. You'll hear me say that a lot as well. So here's sort of the basic concept of sig figs. It turns out that in chemistry, whenever we're talking about numbers, we're not talking about like this symbolic number 4 like we're talking about in a math class. We're always talking about measurements, right? So it's not just 4, but 4 centimeters, for example, or 4 grams, or 4 moles, or 4 liters, whatever it may be. These correspond to measurements, okay? And it turns out that there's a big difference between 4 centimeters and 4.00 centimeters, okay? To a mathematician, they would look at this and say, those numbers have the exact same value. Those are the exact same numbers to a mathematician. Your calculator certainly doesn't know a difference between 4 and 4.00. But to a chemist, those are very different numbers. 4, because this now corresponds to a measurement. So what those digits represent is a certain confidence that you have in that measurement. 4 centimeters says that you're confident that that distance is between 3.9 and 4.1 centimeters. It's somewhere within that range, right? As soon as you tack those 2 extra zeros on the end, now you're saying you're even more confident in that measurement. This would correspond to a measurement that's between 3.999 and 4.001 centimeters, a much smaller range, right? So those extra digits, they represent a certain confidence in this measurement. Like if I'm going to like spitball how far away that back wall is over there, 30 feet. How confident am I in that 30 feet? Not very confident at all. It's not 30.0000 feet. It's like a really squishy 30, right? So the bottom line is the number of digits that we tack onto a number, they say something about that measurement, how good that measurement is, all right? So we're going to have this whole logic behind how we count what are called sig figs and how we propagate them in our calculation. Okay? So, step 1, we are going to learn how to count significant figures. Well, sig figs. All right? This sort of like logic that we're going to apply here, we're going to kind of see over and over again. I'm going to give you this list of rules that how we look at a number and we count figures, sig figs, and then we're going to apply that list of rules to a bunch of different examples. We do that a lot in chemistry. We kind of lay out, this is our logical approach. Let's apply that approach here, there, and the other place. All right? So again, we got this list of rules for how we count sig figs. Number 1, all non-zero digits are significant. Okay, so for example, a number like 3.25, every digit in that number is a non-zero. So every single one of those digits would count as a sig fig. So this number right here has 3 sig figs. Again, that's the name of the game here. We're counting the number of sig figs we see in a given number. 3.25, all non-zeros, they're all significant. Okay? So clearly the zeros are going to be the pain in the butts, right? If it's not 0, we don't have to worry about it. If it is 0, we got a little bit more consideration here. Okay, so rule 2 then. Zeros between non-zero digits are significant. Okay, so if we see a 0 in our number, but it's sandwiched between two digits that aren't a 0, we're going to count it. So for example, 1001, those two zeros are sandwiched between those two ones, so I get to count all 4 of those digits as significant. So this number here would have 4 sig figs. Okay. Leading zeros. So if I have a very small number, for example, 0.005 centimeters, it's got these leading zeros in front of it, zeros to the left-hand side. They are never significant. So the zeros that appear on the left-hand side of a really tiny number like 0.005, they do not count as sig figs. So when I'm counting sig figs in this number here, I'm going to skip over all 3 of those leading zeros. This number right here only has 1 sig fig, that 5. So if they're out front, they never count. If they're in the middle, they always count. And then the big pain in the butt ones are the trailing zeros, the one that appear at the end of a number. So these trailing zeros are significant only if the number contains a decimal. Okay? So if you see a decimal point in that number, then you will count those trailing zeros. If there's no decimal point, they don't count. So let's just do a few examples here because this is sort of the more complicated of all the rules. All right, so in our 4.00 that we were talking about, how many sig figs do we see here? 3, because all those zeros are going to count for me because they're after the because there's a decimal in that number, right? So because of that decimal point that appears, all 3 of these are going to count. But what if I had 400? Now there's no decimal point that appears in this number, so I'm not going to count those trailing zeros. The only sig fig is this non-zero digit out front, that 4. All right, so this number here would just have 1 sig fig. Okay, so this is our rules for counting sig figs here. This is the first step. This is like the first little tool that we have to have in our toolbox before we can do math and in general chemistry here. All right, we got to be able to look at a number and count how many sig figs there are in that number. Okay, so I'm going to put some examples down. You guys are going to go through. You're going to count how many sig figs you see in each of those numbers, and then we'll go through them together. We'll leave our rules up at the top here. So we got 5 numbers up here. You guys are going to go through and tell me how many sig figs you see in each of those 5 numbers. 325. How many sig figs do we see? 3, because we got all non-zero digits, so they all automatically count. No funny rules going on there. 400.25. 5, right? So now these zeros are sandwiched between non-zero digits, so this would be all 5 of those digits up there would count. 15,000. How many sig figs?
2.
All right, there is no decimal in this number here, so the only sig figs I'm going to count are the 1 and the 5. This number here would have 2. So these are an example of trailing zeros that are not significant. And what about if I have 0.002500? How many sig figs do we see in that number? 4. Okay, so let's make sure that we can see this. These 3 zeros right here, do they count? No, because leading zeros never count. So I'm going to automatically just skip over those leading zeros. We got a non-zero digit, and these 2 back here, are they going to count? Yes. Why do they count? Because I got that decimal in my number, right? So if you see a decimal appear in your number, you're going to count your trailing zeros. So I have 4 here. Okay? Now this is something that you would like never ever see in math class here. A number like 6,000 with just a random decimal point at the end here. Okay? Why am I putting that decimal point at the end? Because I want those trailing zeros to be significant digits. So this would be how we would write a number like 6,000 with 4 significant figures. Okay? Why wouldn't I write it 6,000.0? Because that's a different number. Rather, that's the same number, but it has a different number of significant figures. That would be 6,000 with 5 sig figs, right? So you will see this like random floating decimal point at the end of the number, and that's in there so that you know that all of the zeros in that number are significant. All right, check. We got our counting sig figs. The next skill that we're going to need is to know how to round numbers to a specific number of sig figs. All right, and this is very important because basically we're going to have these rules for carrying sig figs. You're going to punch this calculation into your calculator and you're going to get an answer and you're going to be like, I need to round this to 4 sig figs, right? So that's what we're going over right now, is how do we round to a specific number of sig figs. So I'm just going to pick a random example here. We're going to round to 3 sig figs. Okay? It could be any number depending on your calculation. I'm just going to randomly pick 3 for these examples here. All right, so for example, 4.24. We're going to take this number, 4.2445, and we're going to round it to 3 sig figs. So importantly, when I round something to X amount of sig figs, that means that the number I write at the end better have that many sig figs. Okay? So that's a good double check. When you get done, you're going to look at your answer and make sure you see 3 sig figs written on the board there. All right? So what we're going to do is we're going to start counting from the left-hand side, from the leftmost sig fig here. 1, 2, 3. I'm going to round to this position here. All right? This little bar notation over a digit. This is how we keep track of the last sig fig in a number. We're going to see this notation a lot here. All right? So I'm going to round this number to that position there. So I need to look at its next door neighbor. All right? I am only going to look at its next door neighbor. I don't care what's going on back here. Every other number after that next door neighbor is dead to me. It's gone. Don't even going to look at it. All right? In this case, right next door is a 4. So in this case, we're going to what we call round down, which really just means that we're going to keep that number the same. This is 4.24. So 4 and below, we call that rounding down. And really that just means that we don't touch that 4. We leave that 4 on the end of 4. Let's do another one here. 678.533. Again, we're going to round to 3 sig figs here. So I'm going to start counting from the leftmost sig fig. 1, 2, 3. So this is where I'm rounding to here. I'm going to look right next door. In this case, it's a 5. 5 and above, we round up. Meaning that 8 is going to become a 9 here. So 6.79. So 5 and above, that's when we round up. Okay? Nothing too crazy? All right. So let's do a few examples here. I want you guys to try to do these on your own, and then we'll work through them together. All right? All right, so this first one, I'm going to round to 3 sig figs. When I'm starting to count position, I'm going to start at the leftmost sig fig, which means I'm going to ignore those leading zeros, right? Because leading zeros are never significant. So that means I'm rounding to this position right here. Does this number round up or round down? Rounds down, because next door is this 1 right here. So this number rounded to 3 sig figs, 0.00659. Again, at the end, I'm going to look at my answer and see that I have written my 3 sig figs here, right? So this number, because the leading zeros don't count, has my 3 sig figs. Great. Okay. This one here, I'm going to round 1, 2 to this position here. Does this number round up or round down? Up. Now, importantly, because this is a 9, it's going to round up to what? 10. It's going to go round up to 10, which means I'm also going to update this digit right here. So this becomes 0.55. What's wrong with this? There's only 2 sig figs on that number right there. Right? So what do I have to do to make sure that I have rounded this number correctly to 3 sig figs? I need 3 sig figs on the page. So what's going to be that last digit that I put? 0. The 0. Awesome. We're going to tack on that 0. Now I have that same number, right? But now it's displayed with that proper number of sig figs, my 3 sig figs. So these big numbers are kind of the trickiest here. Okay? So I'm going to round 1, 2 to this position right here. Okay? Let me show you the big mistake that people make is they say, all right, that rounds up, right? There's a 9 next door. So this is going to become 1, 5, 5. This number has 3 sig figs, so I'm done, right? If I told you I was going to give you this much money, rounded to 3 sig figs, and I gave you $155, how would you feel about that? You got gypped out of 14,000 some odd amount, right? This is a very different number than this. Don't change the number. This is 15,497.2. So that's going to round to 15,500. I tack those zeros on there. There's no decimal in that number, so those zeros aren't significant. But importantly, I haven't changed the value of that number. If you're starting out with a 1 in the 10,000s place and a 5 in the thousands place, they got to be there in your answer as well, right? So make sure to include those zeros on the end. This is specific to these larger numbers here, but this is a really common mistake that people make, is they just chop off those zeros and they change the value of that number, okay? So again, just think about it in terms of dollars. You'll never get it wrong. Cool. All right, so we got the counting and the rounding down. Before we move on, we're going to go and introduce what's called scientific notation. You can represent any number in scientific notation, but truthfully it's used because it's most convenient to represent numbers that are really, really large or really, really small. All right, and we're going to use this exponent notation. That's what scientific notation is. Okay? So, why do scientists like scientific notation? Well, if I'm going to try to talk about the number of water molecules that are in this bottle right here. Water molecules are super duper tiny, right? This isn't a huge volume right here. This is about a liter. How many water molecules are there in that bottle right there? Something, I'm just going to spitball here, but it's going to be something on the order of That's a good approximation for about how many water molecules are in that bottle right there. This disgustingly huge number with so many zeros at the end that you can't even really look at that number and see how big it is. Your eyes kind of lose track of how many zeros there are up there, okay? So in order to more conveniently represent that same value, we would use scientific notation, 1 times 10 to the 25. All right, that is the same number, but it's using this more compact notation here, and then I can actually see how many zeros there are on the end of that. Okay, so we're going to work with somewhat smaller numbers so we can sort of get a better sense of what's going on here. So if we said, for example, 3.25 times 10 to the 2, okay, we can punch this into our calculator here. What's 10 times 10? Yeah, I believe in y'all's mental math on that one. 10 times 10, 100, right? So this is just punching it into our calculator would be the same thing as representing 3.25 times 100, or 325. This is how we would represent this number in what we call scientific notation. This is what we call standard notation. Let's try to go the other way here. What if I had a number like 4,625? Take a second and see if you can't put that number in scientific notation. So first of all, if we take a number and like 3.25 and we take it and we multiply it by 10 in our calculator, what we're going to see is what that does is it bounces this decimal point over. So if I multiply it by 10 twice, it'll bounce it over twice, which is how I got my 325. So if I'm going to go the other way, I'm just going to count how many steps, 1, 2, 3, I need in order to move that decimal. So 4.625 times 10 cubed. All right, I bounced my decimal point over 3. That's how I got times 10 to the third. Okay. We can also use negative exponents. Negative exponents are a little less natural for people in their mind, but we can use them in scientific notation. You will see them in scientific notation for small numbers. So for example, 1.25 times 10 to the negative 2. All right, again, I'm going to bounce my decimal point here. But 10 to the negative 2, is that a big number or a little number? That's a little number. So I'm going to bounce it the other direction. So at the end of the day, I have a little number. Right? 1, 2 positions here. So this would be the same as 0.0125. So we represent big numbers with positive exponents and little numbers with negative exponents. All right, and that's kind of the first step that I want you to do when you're putting a number in or out of scientific notation is just take a step back and ask yourself, do I have a big number or a little number? Some people try to memorize, oh, if it's positive, bounce to the right, or negative, bounce to the left. The problem is the direction changes whether you're going in or out of scientific notation. So if you want to memorize 4 different rules, go for it. But for me, the easiest thing to do is to just take a step back and ask myself, do I have a little number, which would require a negative exponent, or a big number, which would require a positive exponent? All right? So let's go the other direction here, 0.00497. I want you to put this number in to scientific notation for me. Do I got a big number or a little number? A little number. So right off the bat, I know I'm going to need 10 to the negative something. All right? What's the negative what? I'm just going to count my bounces here. 1, 2, 3. Moves that decimal point into the proper position there. So 4.97. All right, let's just take a look real quick. Okay, importantly, this is a number in proper scientific notation. In proper scientific notation, just like in all of our examples here, can only have one non-zero digit before the decimal. So 32.5 times 10 to the 1, mathematically these are equivalent, but this is not proper scientific notation because you're only allowed to have one digit to the left of the decimal. All right, and because of that, and we can kind of convince ourselves that because proper scientific notation only has that one digit to the left of the decimal, there's then going to be a decimal with whatever comes after it. The nice thing about scientific notation is that all digits are going to be significant. All right, just following our rules of what it means to be a significant digit. If you see any zeros in this number, they're necessarily going to appear after that decimal place, and so they're going to be considered as significant digits, right? So every digit that's displayed in scientific notation counts as a significant digit. All right, so let's do two more examples here, rolling together this concept of scientific notation and of sig figs here. 0.003200 and 15,000. I want you to take a second and put these two numbers here into scientific notation. This first one here, do I have a big number or a little number? A little number. So before I even get started, I know I'm going to have a negative exponent here. Something point something times 10 to the negative something, right? I know that just because I have a little number. Okay? So now I'm going to bounce my decimal point to get it in the proper position. 1, 2, 3. So that's 10 to the negative 3. So 3.2. times 10 to the negative 3. Let me make it a little bit less messy. Am I done? Let's be careful here. How many sig figs do we see in 0.003200? 4. How many sig figs do I see in 3.2 times 10 to the negative 3? Just 2. I need to include those trailing zeros so I don't change my number of sig figs. So not just 3.2, but 3.200. And again, the nice thing about scientific notation is all digits displayed are going to be your sig figs. All right, same thing over here, same consideration, just now we have a big number, so we're going to have a positive exponent, so 10 to the positive something. I'm going to bounce my decimal point to get it into the correct position here and count how many jumps I make. 1, 2, 3, 4. So this is 10 to the positive 4, 10 to the 4th. All right. So should it be 1.5 or 1.5000 times 10 to the 4th? Which one of these two is going to be correct? Let's take a poll here. Let's say A and B. Who thinks it's A? Who thinks it's B? Excellent. So it is going to be A here. If we look at our original number, let me get rid of my arrow here so we can see more clearly. This number was presented without a decimal point in there. So that means that those trailing zeros do not count. This number only has 2 sig figs. So when I put it in scientific notation, I'm going to make sure to represent that number with those 2 sig figs. Okay, so not that one. All right. Again, these are kind of simple numbers. They would have been just as easily represented in standard as in scientific notation. But when we're talking about the number of gas molecules in a room, or if an astronomer is talking about the distance to a star, some huge ridiculous distance, right? That's when the scientific notation becomes really kind of essential. Otherwise, you're printing numbers like this all over the page, which is just ridiculous. Okay, cool. So we got our sig fig tools down here. Now we're going to focus on carrying sig figs. In our mathematical operations. All right? So every operation has different rules. Our operations that we use here in a general chemistry course are either multiplication, division, or addition and subtraction. Okay? So we're going to lump these into different bins. We got different sets of rules. The first one that we're going to go over for carrying sig figs is our rules for multiplication and division. All right, so why is this going to be important? Chemists often, they take these measurements, and again, the number of sig figs in those measurements, they correspond to how confident we are in that measurement. But rarely are we just publishing the naked measurements on their own. Often we're doing an analysis with those measurements, right? We're taking those measurements and we're performing calculations. We're going to punch them into our calculator. Our calculator doesn't know anything about sig figs. Our calculator is always just going to give us a whole bunch of digits for every calculation. But you can't put all those digits in your scientific paper because all of a sudden it's saying like, oh, I have supreme confidence in this analysis here, even though my measurements kind of sucked. So we have to have this way of carrying these significant figures through these measurements. We don't want to over-represent how confident we are in a given calculation, all right? So let's take something like 4.5 times 1.255. Okay? This is not the hardest operation in the world in that we all have calculators that we can use, right? We don't have to do any mental math here. It's not like I have to know what it is off the top of my head. So what we're going to do is first step is to just perform the calculation just like you were in a math class, right? So you're going to get your calculator out. You're going to go 4.5 times 1.255, and you're just going to write down a whole bunch of digits, right? Write down whatever your calculator gives you here. So 5.6475. Okay, so step one is just do the multiplication or division. Check, check. All right. After we do the math, now we're going to go back and we're going to worry about our sig figs. So what we're going to do is count the number of sig figs in each of our inputs. By the inputs, I mean the numbers that you punched into your calculator to get your answers. So the 4.5 and the 1.255, those are my two inputs. So everybody take a second and tell me how many sig figs there are in 4.5 and how many sig figs there are in 1.255, right? Step one for carrying our sig figs is counting the number of sig figs in our inputs. All right, so how many do we see in 4.5?
2.
There's just 2. And how many do we see in 1.255? 4. Okay. So we're going to count the number of sig figs in each of our input, and then we're going to round our answer to whichever number is fewer. Or is less. I think fewer is technically correct, but whatever. meaning I'm going to compare the 2. I'm going to compare the 4. Which one's the smaller number? The 2. So that means I'm going to round my answer to 2 sig figs. So everybody take a second and round our answer here to 2 sig figs. This 5 is a sig fig, so I'm going to round to this position here, the 10th place. So my final answer, rounded to the correct number of sig figs, is 5.6. Right, and again, the point is that we got this calculation here. We don't want to over-represent how confident we are in that analysis, so we got to look at how confident we are in our inputs. Yeah, this number over here has 4 sig figs, but this number only has 2. So my answer is kind of only as good as whichever measurement is worse, which is why I'm going to round my answer to 2 sig figs here. Cool? All right. Importantly, because again, different operations have different rules. If I'm going to summarize these rules for multiplication and division into one word, the one word I want to have in my mind that's synonymous with these sig fig rules, it is counting. Right? That's the basis of how I'm applying my sig figs to my answer, is by counting the number of sig figs in my inputs. All right, so then let's just do a few more examples here. I'm going to put down some problems and you're going to give me the answers. So let's do this first one here. Step 1 is to just punch this into your calculator. I get 0.013212. Right? Putting down everything my calculator gives me, but again, the calculator doesn't know anything about sig figs. So now I'm going to go back and apply my carrying sig fig rules, which again, if I got one word in my mind, it's counting. I'm going to count the number of sig figs in each input. 450 has 3. 1, 2, 3, 4, 5. All 5 of those count in my second input. So how many sig figs should my answer have? Whatever number is fewer, so those 3. Remember, those leading zeros don't count as significant. So 1, 2, this would be my third sig fig that I'm rounding to. So 0.0132. Boom. And this is pretty standard format for what you're going to see in terms of how I do my math. I give you the number that the calculator gives me with the sig fig marked, and then I put my final answer in a little box. Boom, final answer. All right, my next one, I punch this into my calculator, 2.0 times 4.00, and I get 8. I'm done. What's wrong with that 8? It's only got one significant figure. How many should it have based on my calculation? 2, because the 2.0 has 2, the 4.00 has 3. So again, your calculator doesn't know anything about sig figs. You got to go back and apply those rules at the end. So I'm not going to leave this as 8. I'm going to display that number with 2 sig figs, or 8.0. Tack that 0 on the end so I have the proper number of sig figs. All right, and then my last one here, I punch it into my calculator, 0.003925. All right, now, truthfully, you don't really have to write every single digit that the calculator does. You just want to make sure that you have way more than the number of sig figs you're going to round to. 2 or 3 extra digits beyond what you're going to round to. That's the good rule of thumb. All right, so in this case, I can put the last ones on there. Okay, so in this case, how many sig figs are in 1.6500? This has 5. But what about 420? 2. Just 2. There is no decimal point in that 420. If it was written 420 with a little decimal point on the end there, then that would be 3. But in this case, there's only these 2. So I'm going to round to this position here, 4.0039. Awesome. Cool. Congratulations. You survived your first